Hey everybody, this is Team 7, or better known as H2Go, and this is our ECE 4960 technical video of our project for the autonomous water planner. So throughout this video, we will be going through the material list, meeting the team, our motivation behind what we designed and what we wanted to build, the problem that we wanted to solve, the performance analysis, and we will also go through the performance videos of H2Go.
So for the materials, we divided them into two sections, one for base station materials, another for the vehicle materials. For the base station, we had a 2.5 gallon water tank, an RFID reader, the Raspberry Pi Pico W, a Pololu IR transceiver, a stepper motor driver, a NEMA 17 stepper motor, the rack and pinion, the 3D printed base, a 9-volt battery, a 24-volt DC power supply. For the vehicle, we had the Raspberry Pi 5, the 11.1 volt LiPo battery, a 12 volt to 5 volt buck converter, 2 DC motors, the DC motor driver, the LiDAR, the color sensor, the other IR transceiver, a capacitive soil moisture sensor, an ADC chip, and 2 RFID cards.
Our team consists of 3 electrical engineers, Daylon, Jorge, and Steven, and 2 computer engineers, Precious and myself. For our project, we wanted to automate the process of taking care of a plant's needs, so we made an autonomous vehicle to take a plant to and from a watering station.
The problem. Plants need attention or they will die. Plants are beautiful. They add life to living spaces. We want to make them accessible to everyone. The project individual parts worked as expected. We had some issues incorporating the phone application to the rest of the system. We also did not perform any navigation tests to the base with water since we were not able to waterproof our electronics inside of the vehicle. Besides that, our team is satisfied with the overall performance of the device as it shows the proof of our concept of our initial idea.
These were the initial prototypes for the plant pot chassis design. The plant pot went through a few different stages before we ultimately came up with the one that we had for the demonstration. As we can see, this one features just one piece with everything connected. The final design, we had it such that the top was removable. This allowed us to be able to reach the wiring to simplify troubleshooting, because with this initial model, we did have to take everything out if we needed to fix a wire or add a component. This one also featured a wheel at the bottom that was cut out for the caster wheel. This allowed for less space in the chassis in and of itself to house the components that were necessary. So in the final design, we used a much smaller caster wheel such that it could sit at the bottom of the chassis and allow that entire inside area to be used solely for electronic components. As we can see, this does provide a proof of concept of the chassis being able to navigate to the home base as well as obstacle detection. In our initial obstacle detection algorithm, once the chassis encounters something, it will back up before slightly changing direction and then proceeding forward. But as we can see, we encountered issues in that it would detect the obstacle twice, and such it would back up twice as well. The final design of the chassis also ended up being slightly bigger because this one could not fit all of the components that were necessary. We also need to run the navigation as well because although it gets close, when it gets towards the end, we see it completely change direction. Once we were able to work out some of these navigation defects, we were finally able to complete the final design of the plant pod chassis. This displays the app that was used to control it. As we can see, the user is presented with 3 different options for plant types, as well as a help button to show them how to use the app initially. Once one is selected, the moisture level will be updated, as well as to whether or not it is acceptable. As we can see, there's a cup of water, so it was 100% moisture, which we expect, and thus it's acceptable. In this next demonstration, we remove the moisture sensor from the plant pot, and then we put it into a completely dry plant to display that it updates the moisture, as well as begins navigation because it is sensed that the levels are no longer adequate. This is demonstrating the different buttons and that they all work, but with each one, the biggest difference is that the plant type that is displayed will be changed. This also lets us know that the threshold has been changed as well, such that the moisture sensor threshold will only be to that specific plant that was selected.
So in this video, you can see the vehicle navigating towards the base station. The lights that are lighting up on the IR transceiver indicate where the signal is being received the strongest. This allows the vehicle to find the base station. This other video also shows the vehicle finding the base station from a different location. Again, you can see the red lights on the IR transceiver detecting the strongest signal being sent from the base and the vehicle finding its way home. The blue tape underneath the base station is there so that the color sensor knows when to stop. In this video, we will demonstrate how the rack and pinion works, as well as more navigation. As the vehicle approaches the base station and stops, the RFID cards are detected by the reader, and the rack and pinion will go down and open the faucet and then go up and close the faucet. We did not test with water because the vehicle was not yet waterproof. Here is a concept video showing water being dispensed by the RFID card. This video demonstrates the LiDAR's obstacle detection. As you can see, it detects the obstacle, which in this case is our foots in front of the vehicle. The vehicle sees the obstacle and moves back and pivots in the direction closest to the base station.